Ladies and gentlemen, welcome to our session of dynamic macroeconomic modeling. I will be chairing this session. My name is Hakan Eratalay, and according to the plan, I will be also making the first presentation. We will as well have three more presentations from Marina Sandomirskaya, Game Theoretic Modeling of Insider Trading, Mikhail Paknin, Should Natural Resources Be Public or Private, and Sergey Vashenko, Estimating Nonlinear Dynamic Stochastic General Equilibrium, I think, models with moment-based methods. So the presentations should take about 15 to 20 minutes. We will have 5 minutes discussion at the end of each presentation. Feel free to ask questions to our presenters, make them reply, and enjoy the session. So I'll start with my current research. This is one of the papers I'm currently working on. So it's a work in progress, and it still needs development, but it's okay. So the name of the paper is Do Correlated Markets Have More Volatility Spillovers? As you can understand from the title, we are trying to relate volatility spillovers. We are trying to explain volatility spillovers with correlation. Can there be a relationship between these two concepts? So what are these concepts? Let's start with some stylized facts. So it has been observed in the financial asset return series that volatilities are changing over time. So the variance of the series is changing over time. It's not constant. Moreover, it is clustered together. So high volatility periods are followed by high volatility periods, and low volatility periods are followed by low volatility periods. This has been modeled through multivariate Gaussian and multivariate stochastic volatility models, and these are some survey papers. And another stylized fact is the co-moments of the first or second moments. For example, the conditional returns might have time varying correlations. This has been modeled by dynamic conditional correlation gauge, or a correction to that model by these papers, or there are many other papers. And then in the second moments, there might be some relation between different series that has been modeled through volatility spillovers. So this is Jam-Tao is one paper, Longin-Solnik is an applied paper. What we will do in this paper is we will check volatility spillovers, and we will also consider time varying correlations. So what is the motivation? We want to explain volatility spillovers with correlations, and the idea of this paper started when I was discussing with a network theory professor, and we were thinking, like, can we import an idea from network theory? And for example, these are two papers where the relationship depends on how the people are close. Yeah? For example, yawning behavior is more contagious between closer people. Or for example, if a person is more likely to smoke if his close friends are smoking. Can we say that this kind of behavior exists in stock markets? Can we say that between two very correlated stock markets, there are more volatility spillovers? This is what we are trying to model in this paper. So, to have an idea as a very preliminary analysis, and very naive analysis actually, we took the daily return data from the FTSE, the London Stock Exchange, for this period. It gives, after eliminating after synchronizing the data and eliminating the data that has missing observations, we have 85 series of 2,645 observations per each series. The source is Yahoo Finance. What we did here is a vector autoregressive of order 1 estimation, but I restricted the parameters to be non-negative. This is an imitation of a variance model, okay? It's like an imitation of an arch model, basically. What I plot here is the coefficients of other series, okay? So if I'm regressing the first series on others, these are the coefficients of other series, not the first series. And these are the absolute correlations of between the other series. So one is not here. It's the correlations between other series. So what I see here is, when I plug this, I see like there might be a negative relation. So I can't use this. But if I were to standardize the absolute correlations with the row sum, when we see the model, we will understand it better. With the row sum of the correlation matrix, if I standardize, then I see that there might be a positive relationship. And the question is, can I use this to make the models better? And as we will see, it does improve the estimation. So what we do here is we propose the network gauge model in which the volatility spill over between series depending on the absolute value of the correlations. It is related to the spatial gauge models in the sense that the volatility spillovers are weighted by a matrix that's calculated from the conditional correlations. And there is a similar work in the literature where they choose the weights exogenously, like distance between countries, or like from the GDP or from the market value of the stocks. And they also show that their model improves. But in ours, the correlations are calculated from the same data. And what we do is that we compare the performance of net gauge model with the other two existing models in the literature in terms of out-of-sample forecasting of the value at risk. And for two portfolios, the target-free minimum variance portfolio and the portfolio for which we minimize the forecast variance of the return while keeping the expected return fixed. So a brief review of the models. Extended constant conditional correlation gauge model of Jan tau is given by the return equation. This is the return equation, this is the conditional variance equation, and the error term. The conditional variance matrix are like separated to volatilities and correlations. And what we see is that in this model, the correlations are constant. The volatilities are time varying, and with these A and B matrices as non-diagonal matrices. This is what rules the spillovers, volatility spillovers. If they are diagonal, then we don't have spillovers, and it will be just CCC gauge model. And the correlations are constant in this original model, but as it has been shown, it doesn't really make sense to assume that correlations are constant, at least in the international stock market data. The corrected DCC gauge model of ALE suggests that the correlations could follow the dynamics. That's basically an equation like this. I won't get into too much details. The only thing is that to be careful here is that this intercept term is calculated from the covariance of the sample values of VT star. And this is called variance targeting. And this will cause problems in our estimation, and we will show how we fix it. It has been shown in the literature that this CDC or DCC gauge models have negative biases when there are too many series to consider. So to fix that, this paper introduced shrinkage to identity method. We will use that. And we combine this model, and we will call it extended CDC gauge. And it exists in the literature, it has been used. And we will take this gauge model without volatility spillovers as well. In our analysis, we will compare them. So the model that we propose, basically, in univariate terms, series by series, it follows an equation like this. So this part and this part is just gauge 1-1 for each series. The new thing is the volatility spillovers, basically, from other series, but with a weighted average. Okay, so we calculate, there's a coefficient for that, and this is the absolute value of the correlation divided by the sum of the correlations, absolute value of the correlations. And in matrix terms, we can write it like this. So in relation to this model, now our A is, for example, this plus this term here. In terms of spatial gauge model, this is my spatial weight right now. And it is important to have a spatial weight matrix that's not symmetric, because it's it should not be symmetric so that we allow for different effects in the volatility dynamics, right? And these are our weights that depend on the dynamic conditional correlations. This is basically the model. So we could estimate all the parameters in one step, maximizing the full likelihood estimation, likelihood. And we have to have an extra iteration here to calculate the covariance matrix that I talked about, the intercept term. And then we construct the log likelihood and we maximize it. And this is maximum likelihood theory, it behaves well, everything is fine. But if we have too many series, estimating it might be problematic. So what we want to do is we use the iterative maximum likelihood estimation. What we do is we take the correlation matrix to be fixed, something, sample correlation, and then we maximize the log likelihood with respect to the variance parameters. So, and then we derive the conditional variance estimates. We do the same, taking the conditional variance and variance parameters given, we maximize with respect to the correlation parameters and obtain the new correlations and iterate until convergence. Now, this may or may not converge to a maximum point. Okay? So, to guarantee that, we use a line search algorithm that's similar to Jung-Becker-Koopman. So, in each iteration, I check whether the next iteration parameter values maximizes this full likelihood. So, I'm like watching if I'm going in the right direction. The theoretical properties of this estimator is unknown, but as we will see from the simulation studies, it behaves quite well. So what we do is we use this data for the London Stock Exchange FTSE 100, and after synchronizing the data, we have 85 series with length 2645. And some of the series have very high kurtosis for one or other reason, so we do an outlier filter, ample outlier filter. And then we form samples of size 500, like rolling samples. We start with the first observation until 500, sixth observation until 505. Like this, we have 430 samples. And using these samples, we check if our estimator follows closely the full log likelihood estimator. For this, we will calculate the deviations in the conditional variance matrix. So I have an operator here that will basically stack the lower triangular part of the conditional variance matrix. I look at the average relative deviations here basically. And also I will report the mean absolute error and root mean squared error for volatilities and correlations. What we see here are these plots. I chose 4 samples from the 85 series. 721 and 74, they are low kurtosis. It's about 8, basically, the kurtosis. Medium kurtosis is like 14. High kurtosis was around 27, 28. And to see the effect of high kurtosis, I'm adding 2 low plus 1 high, the 33rd series. So, I'm also plotting the kurtosis of each of these 500 samples, okay? And the skewness, the red line, and the black line is the mean deviations. What we see here, although there are spikes, the black line is very much around 0 moment. Another interesting point is that when there is skewness that's far from 0, and when there is high kurtosis, the black line stays around 0. But if there is high kurtosis, while there is no an example here, for example, while there is not much skewness, we see that the black line is around 0. So there is something related to the kurtosis where there are extreme values in both sides of the distribution. And I will be looking at it in further research, basically. So these are the results for the volatilities and correlations. What we see is that median and the mean are quite close to 0 in all cases for volatilities. And the maximum and minimum are quite far from the 95th and 5th quantiles, so it's doing quite well. Same for the correlations. And then, out of sample forecasting, what we do is, for these models, NetGarch, ECDCC, and CDCC Garch models, we compare the models in terms of out of sample forecasting for these 2 portfolios, as we talked about. There is no restriction for long or short positions. The investors can take both. And we consider three target returns for the second portfolio, 0.005, 0.01, 0.02%, which imply a yearly return of 1.25, 2.5, and 5%. And we consider these significance levels 0.5%, 1%, 5%. So what we do is for each of these 500 samples, we do auto-sample forecasting of 1 to 5 days. Okay, so this is like the investor is using the last 500 returns to make a forecast of the next week's returns. Okay, and then after next week, the next weekend, he's updating his forecast, and basically this makes sense. And so what we have is we calculate the number of value at risk violations, okay, for each of these forecasts, and then in total we will have 5 times 430 samples. This many experiment days to consider, and what we expect is that the ratio of the value at risk violations should give me the value of alpha, which is the significance level I'm considering. And the likelihood ratio statistic that's given by this equation is distributed by chi-square 1. So I will be calculating the probability of the statistic from there. So this is a table that's very small, I know. This will go to the paper. Basically, I'm calculating for each alpha, for each target return and target free portfolio. All these first lines are the ratios of violations of value at risk, and second lines are the probabilities that correspond. So let's summarize that. For each model and for each series we consider how many failures to reject there are. Failure to reject means that my value, the ratio of violations of value at risk is equal to alpha. That's the null hypothesis. If I fail to reject, then in those cases the null hypothesis is accepted, not rejected. And as we can see, in some cases the net gauge model might be doing relatively worse, but when we look at the total, it's actually doing quite good and even better than the extended CDCC model. So this is something good because I have less parameters to estimate. I have dynamic coefficients in the model, which gives the flexibility to the model to take into account volatility spillovers that might change over time. Because in the other model, we fix the coefficient, we estimate it, and it's fixed for each time period. And in this case, these are changing over time. So, and it's doing quite good. So what we see so far is that this model is a good alternative compared to the extended CDCC model. And we have less parameters to estimate, we have a good model basically. But of course this is like the preliminary results. We want to consider more series, this is missing right now. And we want to check the robustness to misspecification of the model, like to have the model generated by a VEC gauge or something very complicated and see how it will behave to that. This outliers problem I still have to think about. And there will be an empirical application. And then I want to relate this paper to network theory in the sense that I want to calculate the volatility spillover matrices for each time. And from there, I want to derive some kind of distances between stocks. How soon a shock given to a series arrives to the other series. This kind of distances. This is what's interesting for me. I want to relate it, but we will see what will go. Thank you very much. Will there be any questions?
Maybe I have a question regarding the outliers basically in the sample. Could it be because there was something that affected some part of this series, but not all of them? So, I mean, are there any explanations behind the outliers? Some events that produce them?
That's a good question. I didn't check each of the series, like history of each of the series. Obvious outliers are from the crisis period, but then there are some like firm-specific effects, and there are just in that series there are some outliers. I didn't check specifically. What I'm doing is this sample filter, which is like doing a moving average filter. And it's like not changing the behavior of the data while eliminating that outlier. And it shouldn't have, I mean, it should provide better estimates basically. And yeah, there is like much more things to do in terms of outlier, like the additive outliers or.
Yeah, because some outliers can affect later on
yes.
the others. I mean, through this exactly through this networking.
Yes. No, it's true. I have to look more into the outliers. Yeah. So this is like how the model behaves when there are no outliers. That's it so far. I have to extend.